Hey there! Have you ever wondered how social media platforms seem to know exactly who to connect you with and perfectly predict the people that you might actually know? Are they spying on me? No, they're not spying on you as you get your Starbucks order. What they're actually doing is analyzing data, using what we call searching algorithms.
Essentially, we can say that the scenario can be represented with a graph. No, not those ones. These. Although they look slightly different, they serve the same purpose. These graphs represent objects and their connections as nodes in the graph, potentially being connected by edges in between them. For example, when navigating to a destination using Google Maps, depending on the starting location that you provide, it will identify all the connected streets, or edges, in between your start and endpoints, which are your nodes, giving you the best and most realistic route to follow based on the connections within the graph.
But how does the computer even do that?
Well, the answer to that is graph traversal algorithms, such as the breadth first search algorithm, or BFS. Picture this. You are at Target on Black Friday. Capitalism demands that there are no parking spots within your line of vision, meaning you must search high and low for an empty spot. Do you choose to go all the way down each and every parking row one by one until you find an empty spot? Or do you check the beginning of each row to see if there's an empty spot within your line of vision instead? A vast majority will choose the latter, which is exactly what BFS is, searching broad instead of deep. In terms of a graph, BFS looks for the layer of nodes or vertices closest to the starting point before moving on to anything past it. You can visualize these graphs as a family tree, with nodes above being ancestors or parents, and nodes further down being children or descendants. The first layer would be your grandparents, then your parents, and so on. The searching algorithm will run through the entire graph in this order, taking note of its parent and any offspring. After the graph is completely searched, the machine can then backtrack to determine the shortest path to any given point.
But what does that mean?
For example, I'll relabel the graph, making my ending point or objective the candy. I know that I must go to the cabinet to retrieve the candy, with the cabinet being the parent, and even before that, I must start in the kitchen, meaning the shortest path to the candy would be the kitchen, then the cabinet, then the candy. Even though the kitchen is also connected to the candy through other paths, it's just not as efficient, and shows the algorithm determines the shortest path instead of just any possible path. These searching algorithms are particularly prevalent in social media. For example, Instagram can go through the people that I follow and connect me with others that also follow those same people as well.
So, I guess they weren't spying on me after all. Right. Even as technology advances and datasets continue to grow, we still can't forget about the instances where these valuable searching algorithms appear yet again in our daily lives. At the end of the day, searching algorithms rule the world.